Good evening, everyone. My name is Aditya Sharma, and this is Aircraft Propulsion Course. So we have been through. So we have been through all the week's content of this course. So this session basically would be conclusion of this particular course. So we will just be briefly touching upon all the topics, different topics that have been covered in each week. So 12 weeks are there. So that we have uh, uh, we can revise whatever we have learned through the course of this particular course. Okay. So this is the whole idea of taking this session. And if you have any doubt, uh, so you can always ask them. So we will be starting this session in a few minutes. So wait for a few minutes. After that, we will start the session. Okay, so we can start today's session. Okay, so instructor for the course is Professor Vinay Kulkarni from Mechanical Engineering, and I am Meshwar Swaminathan. Also, I've been the TA for these sessions. So, contents of this session are as follows. Each week's theme has been mentioned. So, initially, we were introduced to gas turbine engines, okay, and the aircraft engines. Then, what we did, we studied Brayton cycle. If you see week 3 to 5, we studied Brayton cycle. Okay. Brayton cycle is the one which is involved in our gas turbines. Right. After that, what we did, we studied different parts of the aircraft engine. So we started with the intake and nozzles. Okay. So intake is air intake for the whole engine, and then at the exit you have propelling nozzle, right? And then in week 8 we saw different types of aircraft engines. Okay. In week 7 we saw different types of aircraft engines, and in week 8 we saw how we can augment the thrust, right? So week 7 and 8 basically are about different types of engines. And then week 9 to 10 are about or you can say week 9 to 12 are about compressors and turbines, right? So broadly, this is the content of whole this 12 weeks course. So now we will touch upon few topics that have been covered in each week. We started with week 1, which is basic thermodynamics and turbo machines. So we were introduced to turbo machines in this week's content, where we started with zero law of thermodynamics, right, which is about which tells about equilibrium, thermal equilibrium. Then first law of equilibrium, first law of thermodynamics, we saw, right, where we equate energy and heat and work, where we equate and we get all the expressions for work and heat through this first law of thermodynamics. Then is your second law of thermodynamics. Okay. So all these are basics about thermodynamics. Then we saw two diagrams. We saw different cycles. Okay. So Carnot cycle has been discussed. Otto cycle has been discussed. Diesel cycle has been discussed. Okay. Rankine cycle has been discussed, which is used in our steam power plants. Steam power plants. Then Brayton cycle is aircraft engines or turbo jet engines. So maybe I can draw a Brayton cycle. Okay. So this is into one. Brayton cycle. In all our numericals, we have been using this PS diagram to solve our numericals. So it becomes very essential that we make ourselves well versed with these diagrams so that we can solve numericals easily. So 1 to 2 is your compression. This is combustion. This is expansion to turbine. Okay. So this is your Brayton cycle. So then turbo machines have been introduced to us. So what is a turbo machine? So there is some machine is there which works on this rotation. Okay. So turbo is from uh, that. Turbo word is from that. From rotation from rotor. And classification of turbo machines is there. So there are two fundamental types of turbo machines. One is which is taking power, one is which is giving power. So your compressor is taking your work input, okay, and your turbine is giving your work output. Right? Then other classifications are also given in week one's content, but we'll keep it to this much only for this session. Okay. Then types of turbo machines. So here the categorization has been done this way. One is your water based. One is your heat based. Okay. So these two types of turbo machines have been discussed, and in these two, again further you have here pumps and turbines. Here you have compressors and turbines. Okay. So this is types of turbo machines that we have. This is about week one's content. Okay. Thermodynamics and turbo machines. Then week two is on gas turbine and aircraft engines. This is week two, gas turbine combustion. So gas turbine combustion, what happens in gas turbine combustion? So this is what happens in gas turbine combustion. This is here only from Brayton cycle. You can know what happens in gas turbine combustion. And the processes involved in it. So it's a constant pressure. So this is basically combustion 2 to 3. It's a constant pressure combustion. During the combustion, the pressure will remain same in ideal conditions. Then there is open and closed gas turbine power plants. Which is for gas turbine. What is open gas turbine power plant? In open gas turbine power plant, the same working fluid will not keep on moving in this cycle, the Brayton cycle. So you'll have compressor, you'll have combustion chamber, you'll have turbine. Here, the working fluid or hot gases that you get from the combustion, they are not going to come again to the compressor. Okay. This is your open gas turbine power plant. Then closed gas turbine power plant. So what happens here? The same working fluid will keep on moving in the cycle. Okay. Now, the thing is that we want to have heat. in the picture in our cycle. So in the open GT power plant, what we were doing, we were giving heat through combustion only. But here we will not involve, and we were involving the working fluid in combustion in the open gas turbine power plant. But in closed turbine power plant, we will not involve the working fluid in combustion. Okay, or heat that we are getting, we will not involve working fluid in it. We will have a heat exchanger here. We will have a heat exchanger. Okay. And also pre-cooler. So after compression, the heat, the working fluid will go to heat exchanger, and then it will go to, after increase in its enthalpy, it is going to go to turbine. And after it passes through turbine, again it will be going to pre-cooler. Okay. From pre-cooler again, it will move on to compressor. So this basically is a closed gas turbine power. Then is gas turbine attachments. So gas turbine attachments, so one is your heat exchanger. Okay. One is your intercooler, the major ones I am discussing, and one is your reheater. Then in shaft and in spool arrangements. So these types of attachments are there. So heat exchanger, what happens in heat exchanger? So the heat from the exhaust gas is being given at the exit of the compressor. Okay. So what it does and why we are doing it, it basically increases the efficiency of your whole cycle. For an open cycle, it is going to increase the efficiency. So what is the function of intercooler? Okay, so intercooler reduces the work input in your compressor by cooling the air that is. So if we have stages in compression, okay, if we have two, three compressors and we are doing it this way, compression of the air. So add some compressor at the exit of some compressor, we use this intercooler, okay, to reduce the heat of the air that is coming out of the compressor. Okay, this helps to reduce the work output in the compression. And the same way, reheater, what it does, it increases the power output. Okay. Then twin shaft and twin spool arrangements. So twin shaft arrangement, what it does is, it is suitable for variable speeds of turbines. Okay, so we are using, let's say, two turbines. Okay, and we want to use these two turbines for two different purposes, and we want their speeds to be different. In that case, this twin shaft arrangement here. Same is than for your compressors. Okay, we are using two different compressors, let's say. So we want compression different speeds for these two compressors and compression different for these two compressors. Okay, so what we will do is we will use this twin spool arrangement. Okay. So this is gas turbine attachments. Then is your engine performance parameters. So a lot of parameters have been discussed. So engine performance parameters. I can draw and display this diagram. The rest can be handled. This is your engine where air is entering, air is exiting. Here is the surrounding pressure, mass flow rate at inlet, velocity at inlet, pressure at inlet, then pressure at exit, velocity at exit, and then this is the exit area AJ jet. Okay. So here you can get thrust here as mass flow rate of air CJ minus EA plus AJ EJ minus EA. But because here fuel will also be involved, so later what we do is we change it to mass flow rate of air 1 plus F. F basically is fuel to air ratio. This is thrust. Then there are other parameters like propulsive efficiency, energy conversion efficiency, overall efficiency, thermal efficiency. And specific fuel consumption is there. What is specific fuel consumption is basically mass flow rate of fuel to thrust. So this is there. Okay. Then different engines have been just introduced. Aircraft engines. Engines like piston prop, turboprop, turbofan, turbojet, ramjet. So piston prop is where you'll have a propeller to drive your aircraft. Okay, and this propeller is being driven by a piston engine. Turboprop is where you have a combination of a propeller and then a jet turbine. Okay, so this basically is turbo prop engine. Then turbofan engine is there. Where so first turbojet, turbofan. So what happens in turbojet? So propulsion is through your jet velocity, okay, velocity of the jet, and turbo is for your turbines. So we are using a turbine here and jet velocity to for providing the propulsion to the aircraft. And then what is turbofan? So in turbofan at the entry of this engine, we have a fan. Okay, so in turbojet you have direct intake. Okay, in turbofan, in turbojet you don't have any fan in the front of the engine, and in turbofan you have a fan in the front. So this fan takes the air from surrounding. Some it passes through the engine, the core where you have it meets the compressor. Okay, and some is air is bypassed. Okay, so some air is bypassed. Okay, let's say this is the core engine. We will have a fan here. So some air will be bypassed. Okay, and this some air will go to your core engine. So this basically is your turbofan rig. Then ramjet is there where you don't have a compressor. Okay, or for that matter, a turbine. And this is used for supersonic speeds, your ramjet engine. Okay. So these are different engines that have been introduced in this week two student. Then week three is there, where Brayton cycle, air standard Brayton cycle has been discussed. So what has been discussed in your air standard Brayton cycle? In your air standard Brayton cycle, you have heat and work interactions have been discussed. Estimation of state variables. Okay. Then optimum work output. Then efficiency. All these things have been discussed in your air standard Brayton cycle. Right. Then you have Brayton cycle with non-ideal components. So ideally, the TS diagram should be like this for Brayton cycle. But then with your non-ideal components, With your non-ideal components, what happens is so with your non-ideal components, your Brayton cycle looks like this. Okay. Ideally, it has to be, so if you see compression, ideally it has to be isentropic from 1 to 2 dash, but in non-ideal cases, it is not like this. The path is from 1 to 2, okay, which is not isentropic. Then if you see the expansion to turbine, so ideally it should move from 3 to 4 dash, but then it is moving from 3 to 4. So this is your expansion in non-ideal case. Again, then heat and work interactions. So all this discussion has been done in this week's content. And then component efficiencies. What is compressor efficiency? What is turbine efficiency? All this has been discussed. What is optimum work output? So all this discussion has been done in this week's. Then we move on to week 4. So in week 4, Brayton cycle with, so he had seen the attachments. So if you see, week 2, so gas turbine attachments we saw. And then now in week 4, we will see these attachments with Brayton cycle. Okay. Through Brayton cycle, we will see these attachments. So you have Brayton cycle with heat exchanger, Brayton cycle with reheating, Brayton cycle with intercooler, and then Brayton cycle with all attachments. So let's see with heat exchanger. So this is week 4. So PS diagram for Brayton cycle with heat exchanger is this. So this heat exchanger here you have, here gas you have. Okay. So this is your Brayton cycle with heat exchanger. Brayton cycle with heat exchanger. Then you have Brayton cycle with reheating. What happens here? So this is reheating this. This is combustion chamber, this is compressor, this is turbine. Okay. This is again expansion through turbines. Okay. So this is Brayton cycle with reheating. Then you have Brayton cycle with intercooler. So this is, you have first low pressure compressor, then high pressure compressor, air combustion chamber, air turbine. So from moving 2 to 3, the intercooler has been used. Okay. So using this intercooler, the work input for the compression reduces. Okay. So this is your Brayton cycle with intercooler. Right. So this is about Brayton cycle with different attachments, and if you have a heat exchanger, reheater, and a intercooler all in one cycle, so all these diagrams can be combined, and then you can get one single diagram. Okay, so this is week number 4. About Brayton cycle with attachments. Okay, so in week 1 we saw thermodynamics and turbomachines. In week 2 we saw introduction to gas turbine and aircraft engines. Yes. Then in third week we saw ideal and non-ideal Brayton cycle. Then in fourth we saw this Brayton cycle with different attachments. Now week 5 is on real cycle. Stagnation conditions, isentropic efficiency, polytropic efficiency. So why we are introducing stagnation conditions, this topic basically is because in the previous discussion, what we were doing, we were taking static temperature, static enthalpy. Okay. But in reality, this velocity is also there with the flow. Okay. So this has to be considered in your enthalpy. Right. So in that case, your stagnation conditions we need. Okay. So in place of T1, we will have T naught 1. In place of H1 enthalpy, we will have H naught 1. H naught 1 is basically representation of stagnation. So this is stagnation. Then is your real cycle. So again, in real cycle, what will you have? You'll not have isentropic compression or isentropic expansion in turbine. So all these things will not be there. Also, there will be losses. Okay, at the combustion chamber, you'll have a pressure loss. Okay, so this basically is a real cycle. Then one important topic that we discussed here is, so isentropic efficiency. Till now we are having efficiencies of our components like compressor and turbine through isentropic supposition. Okay. Or through isentropic conditions we imagine, and then we try to have the ideal case and we compare it with the real case. But then if we want to have instantaneous efficiencies, okay, so for that case we use polytropic efficiency. So this is what I was saying, that based on the polytropic efficiency, we can compare two different compressors of different specifications. So we bring its pressure ratio to one value, and then based on the polytropic efficiency, we can tell which one is more efficient. So this is polytropic efficiency. So this is week 5's content. Then week 6 content is on intake and nozzles. In intakes and nozzles, first we have discussed nozzles. Okay. Then intakes we have discussed. So in nozzles, if you see, this is week 6. In nozzles, if you see, nozzle basically is to accelerate your flow. Okay. At the exit of the engine, at the end of the engine, you place a nozzle to accelerate your jet or gases that are coming out of the turbine after expansion. So you want to accelerate these gases to have the jet with the maximum velocity, okay, so that it can be used for propelling the aircraft. So I'll just draw a CD nozzle. I've drawn a CD nozzle. Convergent, divergent nozzle I have drawn. So, first topic I have written is area velocity relation. How the flow will behave in a nozzle or in some duct, this relation tells that. So if you see this equation, it says that if your Mach is greater than 1, so it means m square minus 1 will be positive. Yes. And in such cases, if your area is, as the flow is moving, as the flow is advancing, if the area is decreasing, so dA will be negative. So du will also be negative, which means your velocity will reduce. So for supersonic cases, the divergent duct will reduce the velocity. This is what the relation is saying. The same way, if you see subsonic, so if m is less than 1, in that case, m square minus 1 will be negative. If it is negative, in that case, if you see dA if increases, or say dA is, let's say again reducing a converging cut. So previously I said dA is reducing, for that mistakenly I said, I believe divergent cut, but I meant convergent cut. Convergent, where area is reduced. So again, now for this m is less than 1, if we again say that dA is negative, which is the area is decreasing, in that case, what will happen? So dA is negative, right? So right hand side will also be negative. But because we already have m square minus 1 as negative, which means du will be positive. So du will be positive, which means the velocity is increasing. So for subsonic flows having a passing through a converging duct, the velocity will increase. So this basically is area velocity equation. Then flow through nozzle. So what happens in flow through nozzle? Basically, you have some pressure here, initial pressure, and then some back pressure is there. And because there is a difference, P naught is greater than PT. So you'll have some flow. So what happens is you have flow. Okay, you reduce the back pressure, the velocity increases. Okay, so let's say this is flow is moment. Okay, so this is flow. But as you keep on reducing the back pressure, so there comes one such moment where your throat gets choked. Okay. So beyond this, you cannot increase the velocity at the throat. And what is this velocity? So this is Mach 1. So at choke conditions, your throat will have Mach 1. So this is one thing. Right. Then what happens is at some cases, you reduce the back pressure, you reduce the back pressure. Yes. So let's say your flow is at this point and it has not reached the exit. So it is at this point. Now what happens is because your flow is accelerating, it means its pressure, static pressure will, its dynamic pressure is increasing, which is there in velocity, but its static pressure is reducing. So your static pressure reduces, and it becomes less than your back pressure, right? In this case, so this case is basically what we call as overexpanded flow. Okay. So your flow has overexpanded, right? And in case your exit pressure is still greater than your back pressure, then we say this is underexpanded. Okay, so there is still possibility of expansion of this flow. So that is clear. So this is your nozzle. Then intake and mass flow rate. So here aircraft engines intake has been discussed. It says that at high speed you'll have low mass flow rates, and at low speed you'll have high mass flow rates. Okay. And then for supersonic intakes, you have three modes of operation. One is subcritical, one is critical, one is supercritical. So in subcritical conditions, your shock will be in front of your air intake. In your critical case, it will be just at the entry, and in the supercritical case, this will have this oblique shock here and this one shock inside the your intake. Okay, so these three modes of operation are in supersonic intake. Then for your propelling nozzle, so nozzle that is at the exit. Okay. So for this, you have efficiency, expression for efficiency. So propelling nozzle. So here, its isentropic efficiency is given as T naught 4 minus T5 divided by T naught 4 minus T5 dash. Okay. So this we have done numericals on using this efficiency of nozzle, where it is expanding from state 4 to state 5. Also, then conditions have been discussed when your nozzle is choked and when your nozzle is not choked. Okay. So this is it about week 6. Then after that, week 7 is there. Where aircraft engines and their examples. So this has been discussed. So turbojet engine, turbofan engine, and ideal ramjet engine. So I'll just draw the schematics of these different engines. So first we'll have a turbojet engine. It will have a intake, then it will have a compressor, then it will have a combustion chamber. So we were discussing aircraft engines, week 7, and I have just drawn the different components of a turbojet engine. So flow will move this way in a turbojet engine. Then there is turbofan engine. So as in week 2, I have already said that we'll have a fan. Then we'll have a compressor here. Then we'll have a combustion chamber here. And a turbine. then in order. So here you have bypass. After this is fan nozzle or cold nozzle. Here this is hot nozzle. Okay, this is nothing. This is a compressor, this is a combustion chamber, this is the turbine. So this is your turbofan engine and its components. Then if you see your ramjet engine, so your ramjet engine somewhat looks like this. So this is your basically intake. Then you have burner here. Then this is your nozzle. So the compression in ramjet engines takes place through this. There is no explicit compressor. Or a turbo machine is there. There is no such case in a ramjet engine. So this is the ramjet engine. Then you have week 8, where you have thrust augmentation is after burning Euler's turbomachinery equation. So in augmentation, we saw that there are two ways to increase the thrust. Okay. One way is to increase the turbine inlet temperature or to increase the mass flow rate. So through increased mass flow rate, if we want to have thrust augmentation, for that we use liquid injection. We use liquid injection. And then through heat, if we want to increase the heat at the entry of the turbine, we use afterburner. So for your afterburner, how this Brayton cycle looks like after burning. how the Brayton cycle looks like. So it looks like this. So there are two cases. If you are using afterburner, so this is with afterburner case, and this is without afterburner case. So with afterburner, first expansion will take place from 3 to 4, then next expansion will take place from 3 to 6 to 7. And in case there is no afterburner, the expansion would have gone from 3 to 5. 3 to 4 to 5. So this is basically nozzle flow with afterburner flow with afterburner and without afterburner. Okay. Then you have Euler's turbo machinery equation. So what is Euler's turbo machinery equation? Euler's turbo machinery equation gives us expression for torque and power in the turbo machines. So this is mass flow rate R2 CW2 minus R1 CW1, where W is for this whirl velocity. Whirl velocity means tangential velocity. So if you have this as your shaft, so the velocity in this direction is axial velocity. If you see the top, then one velocity will be just perpendicular to this sheet. That is tangential or whirl velocity. One will be radial. R radial E omega E axial. Or C, you can write C also. So this is there. Then power, if you want, power is force into velocity. In rotational mechanics, it is torque into angular velocity. So this is R2 CW by W minus R1 CW1 into W. This becomes Q2 CW2 minus V1 CW1. Okay. Yeah, U basically is the blade velocity. So this is it about week 8. Then next we have compressors, turbines to discuss. So before discussing these, we'll take a short break and then we will continue the session. Thank you. Okay, so let's continue the session. Then like velocity diagrams will draw for a centrifugal compressor. Then expression for degree of fusion. So week 9 is on centrifugal compressors. So first diagram we have is this. From the lectures, first diagram we have is this. So this is for impeller of a centrifugal compressor. Okay. First of all, these velocities, CBU. This is absolute. This is relative. Okay. It is for your rotor or shaft or blade speed we call it also. So this is there. So C1 is there. You have absolute velocity. Okay. So it will have two components. One will be axial component and one will be tangential component. Okay. Then at the exit, if you see, your flow is in radial direction. So if this is the shaft, the flow will be in this direction. And this is your U2 is your blade velocity. And then alpha and beta are given. Okay. So alpha is with your U and C, and beta is with your B and U. So if you see here, this is alpha one, this is beta. Then what is discussed? Forward and backward vanes. Vanes have been discussed. So how they are different from each other, that we can tell from the velocities that we get from these two types of vanes and inlet. This is V1, this is C1. And this is C2, this is C2, this is CR2, this one is U2, this is ball velocity CW2. So the difference, when you draw the second one, then we'll see. So I have drawn first backward, then I'm drawing this is. So if you want to have the radial and tangential, so you can just draw that. Okay, skip that. So the difference comes here in the blade angle beta 2. Okay, so the difference comes in your blade angle beta 2. So in your backward range, beta 2 is less than 90 degree, which I believe we called as acute angle. And for forward range, your beta 2 is greater than 90 degree, which I believe we call obtuse angle. So these are the velocity diagrams or velocity triangles. Then often degree of reaction is asked, okay, in the questions in the exams. So for a centrifugal compressor, degree of reaction is, so degree of reaction basically is the enthalpy change in impeller to the enthalpy change in the whole stage. Okay. So this lambda is 1 minus CBW2 by 2 U. Or this is also equal to one minus phi 2 cot alpha 2 by 2. This is the okay. This is flow coefficient, which is CR2 by U2. So this is there. Then next week is on axial compressor, axial flow compressor. So here are the velocity diagrams. Let's see. Okay. I'll give the combined velocity triangles. So at the inlet, what happens at the outlet of this compressor. Okay. So this basically is your rotor. For your rotor, at the inlet, what happens, and at the outlet, what happens. So you have a rotor, then you have a stator. Okay, in your axial flow compressors. Then velocity triangles you'll see. So this is your blade velocity u that remains same for a particular height. Okay. So these discussions are on mean height of the blade. Right. So I hope you remember you have one blade. Okay. So this is like this. So you have one blade mounted on a shaft. Okay. So this is mounted on a shaft. This blade. At some cross section, we are analyzing these velocities. Okay. Then what happens at inlet? You have this absolute velocity. Then you have this relative velocity. This is alpha 1. This is beta 1. Then this is alpha 2. This is beta 2. This is B2. This is C2. Your absolute velocity will divide into axial direction and tangential direction. So there is no radial component involved. So I have been repeating this again and again that it is very important that we are able to imagine the velocities, otherwise we'll not be able to understand the velocity. This is CW1. I've tried my best that you are able to visualize these velocity directions in the tutorial session. So if you still are having some issue with visualizing, you can always reach out to me, or you can just type in the comment box. I'll be happy to answer. So this is the velocity triangle for your axial flow compressor. Then degree of reaction, if you see. So enthalpy change in your rotor to enthalpy change in your whole stage. So this is 1 minus A tan alpha 1 plus tan alpha 2 divided by 2. Also, if lambda is equal to half, in that case, your alpha 1 is beta 2 and beta 1 is equal to alpha 2. That is C1 is equal to V2 and V1 equals to C. So this is about degree of reaction. Then there is free vortex condition. So why we are discussing free vortex condition? So we want that there be radial equilibrium at different blade heights. Then we are analyzing the flow. So we want that radially there should be no flow. Okay. So when we take such supposition, we reach out to this condition, which is free vortex condition. And this is RC omega is equal to constant. So if we can keep this multiple R of R and C omega constant at different blade heights, okay, at different positions on the blade along its height, so we can maintain the radial equilibrium. So this is basically free vortex condition. This is basically what is the context of pneumatics release. Then you have leak number 11. So leak number 11 is on turbine. So axial turbine, radial turbine, and their examples. Your axial turbine will have a draw a combined axial turbine will have a nozzle and a rotor. Then the velocity diagram. Its velocity diagram is this. This is blade velocity V2 C2. This is C3 V3. This is axial velocity CA3. This is axial velocity CA2. These axial velocities are same across the rotor blade in an axial flow turbine. Then if you see the if you see the V2, its tangential component is this. And for C3, the tangential component. So tangential component has reduced as the flow goes across the rotor. Okay. Then this is a velocity diagram. Then degree of reaction. Expression for degree of reaction. Yes. So across the rotor, what is the enthalpy change? And across the whole stage. So for this, we have this formula. Tan beta 3 minus tan beta 2. Or lambda is equal to half of phi, which is flow coefficient, tan beta 3 minus tan. Okay. And for if lambda is equal to half, in that case, your beta 2 is equal to alpha 3 and alpha 2 is equal to beta. So this is degree of reaction for your axial turbine. Then you see radial turbine, inward flow radial turbine, inward flow radial turbine. So for this, at inlet you have this, at outlet you have this. Let's draw. At outlet you have this. So this is V3, C3, CR3. This is W3, this is V3. So these are the velocity diagrams for your inward flow radial turbine at inlet and outlet. So, and if you want 90-degree inward flow radial turbine, in that case, your beta 2 will be for, I'll just write it here. For 90-degree inward flow radial turbine, what is the condition? Condition is beta 2 is 90 degree and alpha 3 is 90 degree. Alpha 2, this is beta 3. Okay. So this is there. Then degree of reaction. If you see degree degree of reaction, lambda is equal to V3 square plus V3 square minus V2 square divided by 2CW. This is your degree of reaction for inward flow radial turbine. This is enthalpy drop in rotor divided by enthalpy drop in stage. So this is about your week 11. Then week 12, if we see. So cascade. So what is a cascade? So till now we have been studying a single blade and the velocities, how the velocities change across these blades. Okay, these rotors across these rotors, be it for your centrifugal compressor, be it your impeller across the impeller, what happens? Be it your axial flow compressor across its rotor, what happens? Be it your axial flow turbine across its rotor, what happens? Okay, and then here is uh, radial flow turbine. Okay, across its rotor, what happens? So, but in that case, we have been dealing with single blades. But then in reality, you have a number of blades. Okay, number of blades on the shaft. If you see along its circumference, you have a number of blades out there. Okay, so your these blades adjacent this arrangement of blades. So this is of two types. One is this straight or rectilinear arrangement, which is called. So this arrangement basically is called number of blades is called cascade. So this can be straight which is called also rectilinear cascade. Then one is annular cascade, which we see in our actual cases. Okay. Then cascade tunnel basically is a type of wind tunnel which is used to study the flow in the cascade across the cascade. Then in the turbine cascade and in the compressor cascade, what forces are involved? Okay, lift and drag forces. So all this has been discussed in this content. Then comes the cooling of your turbo machines. So why do we want to cool basically is so as if we keep on increasing the inlet maximum temperature or the inlet temperature of the turbine, it helps to increase the efficiency of our whole system, of our whole cycle. Also, it increases the power output. Okay. So for that, we take two types of cooling methods. One is internal cooling method and second is external cooling method. So we, in internal cooling method, we have passages in our blades through which we pass air coming from the hub. So this comes from hub and goes to the root of the blade, and from there it exits at the tip of the blade. So this is internal cooling method. And in external cooling method, so this air moving from passages, we let this air to pass through the surface of the blades also. Okay. So this is basically external cooling. So this is it about week 12 and about this course also. So briefly then if I conclude, so week 1 and 2 was basically introduction of thermodynamics and turbo machines. Okay. And then what types of turbo machines are there? So all this was discussed. And then basic engines were also discussed in week 1 and 2. Then week 3, 4, 5 were on sorry. So week 3, 4, 5 were on Brayton cycle. Okay. Then you have week 6. So from week 6 onwards, we are taking components of the gas turbine. So week 6 was on your nozzles and intakes. Then the week 7 again is week 7 and 8 again are on different types of engines. Okay, so we have in detail, we see the configuration of different types of engines in week 7. And then in week 9 to 12, we see compressors and turbines. So this is it about aircraft propulsion course. So I hope this was a learning experience for you all, and I wish you luck for your coming exam on this particular course. So thanks for watching this session. Bye.